Hey everyone, welcome to the lecture. Today we're going over ocean currents. We're going to be here for a hot minute before we get into watershed stuff, so buckle in, enjoy the ride. This is going to go with the vocab, and I've allotted for you to have about 2 days worth of work for this, so there's going to be a bit here, but I know y'all can handle it. Here's a joke for you if you want to pause all this. So ocean currents, circulation, it's the water movement in the ocean. Currents, they are cohesive streams of seawater that circulate through the ocean. So the ocean is not just one big tub of water. It is lots of different rivers and streams and pockets of water that are constantly moving around each other, if that makes any sense. Currents are also water masses in motion. So water mass, a body of water identifiable from its temperature, salinity, or chemical content. So upper water mass includes the well-mixed surface layers of the ocean and the thermocline. Thermocline is a boundary where you have two different water areas that are two different temperatures. Deep water mass includes the water below the thermocline to the bottom of the ocean. So, say that this is your ocean right here. Your thermocline would be right here. Everything above would be, say, 60 degrees. And then that doesn't even look like 60. And then everything below would be much colder. Just to give y'all a visual. Why is it? There we go. Okay, so the ocean is forced from the surface by fluxes of momentum and buoyancy, heat, and fresh water. Surface currents are influenced by major wind belts, and then currents redistribute global heat. This is why the West Coast is much cooler and the East Coast is much warmer. Most of the stratification is in the top kilometer or so. Thermohaline circulation affects deep currents. That's your temperature salt barriers. The sluggish thermohaline circulation forces ocean overturning, reaching in some regions to the sea floor, resulting in the formation of the major water masses of the global ocean: North Atlantic deep water and Antarctic bottom water. So currents affect marine life. Some marine life will follow ocean currents, like Nemo and the turtles. Some marine life that's how they know to migrate, that's how they know to reproduce, that's how they know what time of year it is. So types of ocean currents. On the surface, you have surface circulation, wind-driven, warm and cold currents, faster movement, primarily horizontal motion, and 10% of the total ocean water. Deep currents are thermohaline circulation driven by differences in density caused by differences in temperature and salinity. And then you have sluggish movement. They're much slower than your faster moving surface currents. They're also much colder. They're vertical and horizontal motions and 90% of the total ocean water. So surface ocean currents, they transfer heat from warmer to cooler areas, similar to pattern of major wind belts, and they affect coastal climates. Deep ocean currents provide oxygen to the deep sea. So ocean currents are driven by the following. You have solar heating, wind, gravity, and Coriolis. This affects of ocean currents. They transfer heat from tropical to polar regions. They influence weather and climate, and they distribute nutrients and scatter organisms. These are all very important things. Solar heating is the distribution of solar heating is not uniform. That made no sense. Solar heating is not uniform. It's so the ocean kind of helps reevaluate that or redistribute. The equator receives more heat than the polar regions because it stays closer to the sun more often. So solar heating causes water to expand and move. Wind is caused by pressure gradient force. Pressure gradient force results in a net force that is directed from high to low pressure. The variation of pressure is caused by differential solar heating. The Coriolis force modifies the movements of the wind, creating global wind belts. Surface currents are wind-driven circulation. So these are your wind belts right here, and they show which direction the wind's going to move in. Typically, you have your northeast trade winds, your southeast trade winds, your westerlies, and your polar easterlies. So gravity, this will pull water downhill or pile against the pressure gradient, high, low. This causes geostrophic current together with Coriolis force, which we're going to get into in a minute. This influences tides. So the moon influences gravity, which also influences tides. Coriolis force is caused by Earth's rotation, faster at the equator than at the poles. This changes the intended path of all moving bodies, winds, and currents. Motions are deflected from right in northern hemisphere and left in the southern hemisphere. This causes gyres and wind belts. So, Coriolis force is caused by the Earth's rotation. It changes the intended path. So it's going to make all these little circles right here. Your direct methods for measuring surface currents. There's floating devices tracked through time. You have a fixed current meter. You have indirect methods such as pressure gradients, radar altimeters, and Doppler flow meters. We might get into these later. So, measuring deep currents, you have floating devices tracked through time. So you have chemical tracers, you have titanium, you have chlorofluorocarbons. These are like your colored dyes that you would use to trace through stuff. And then you have characteristic temperature and salinity. Then you have Argo. So Argo is a global array of free drifting profilling floats that will measure the temperature and salinity of the upper 2,000 meters of the ocean in near real time. These are all your floats, all 3,260 of them as of October 27, 2009. So surface currents, they occur above the phenocline. Frictional drag between wind and ocean. They generally follow wind belt pattern. Other factors, you have distribution of continents, gravity, friction, and Coriolis effect. So gyres, these are large circular loops of moving water. They are bounded by equatorial current, western boundary currents, northern or southern boundary currents, eastern boundary currents. They are centered around 30 degrees latitude north and south. So, gyres are like continents to your smaller currents being like countries, if you can get that analogy. Gyres are like currents, currents are like countries. So, you have this big gyre right here, that would be like Africa, and then you have smaller currents within that operate within that gyre. So you have your five subtropical gyres. You have the North Atlantic Columbus Gyre, South Atlantic Navigator Gyre, North Pacific Turtle Gyre, South Pacific Hadrol Gyre, I'm not even sure if I'm saying that right, and the Indian Ocean Majid Gyre. Then this shows you, this is like your total gyre, but these are the currents within those gyres. So like continents and countries. Four main currents flowing into one another. You have your equatorial currents, north or south. They travel westward along the equator. Western boundary currents, these are warm waters. Northern or southern boundary currents, easterly water flow across ocean basin. And you have eastern boundary currents, these are cool waters. So gyres and boundary currents, you have North Pacific Turtle Gyre, you have the North Atlantic Columbus Gyre, and these are all the currents within those gyres. You can pause it, look at it. Quite interesting. I'm not going to get into all that. So equatorial countercurrents, eastward flow between north and south equatorial currents. Then you have subpolar gyres. These rotate opposite subtropical gyres, smaller and fewer than subtropical gyres. Then you have subpolar currents. You have your North Atlantic, Norwegian, Labrador, and East Greenland. And then you have your Southern Ocean, you have your Antarctic circumpolar, and then you have the North Pacific, you have the Alaska, Aleutian, and Ohio. So the westward flow of the equatorial surface wind produces anticyclonic current gyres. They start with north equatorial and south equatorial currents in the North Atlantic 1 and 2, and Pacific 3 and 4, and then Indian has 5. So these are the westward flow of equatorial surface wind produces anticyclonic current gyres. These are blocked by land. These currents turn poleward. So you have 8, 9, 10. 8's going to be your Gulf Stream. That's a major current for us. It keeps the East Coast warm. It makes fishing good in the North Atlantic. Then you have, they cool down on the other side. This is why we have cold water in Washington and Oregon and the northern part of California are so cool and cold and productive, and everything is because they have the California current. So it starts out really cold up here, bringing all that Arctic water down, and warms up as it gets down to Baja. This starts out really warm down here in South America and cools off as it gets up here towards Canada. Same thing with all these others that you see. So Earth's rotation produces the Circumantarctic or circumpolar current, also called the westward drift. This cold water current is the only ocean surface current that joins the waters of all the oceans. Equatorial countercurrent is the gravity-driven rollback of warm water stacked on western margins of the tropical ocean by westward flowing equatorial surface wind. Understanding the formation of surface currents. So things to consider: Ekman spiral and transport, convergence and divergence, vorticity, and geostrophic balance. We're going to get into all of these, so don't worry. So your Ekman spiral. The spiraling pattern describes by changes in water direction, speed, and depth. Surface currents move at an angle to the wind. The result is a surface flow of 45 degrees to the right in H. Direction varies and velocity decreases with depth until 100 meters, direction of frictional influence, depth at which motion ceases. So basically there's your surface current. As you go down, it's going to shift to the right by 45 degrees until you're going pretty much at a 180 at 100 meters. So you can see that right there. So factor, wind pushes water through wind stress, and Coriolis effect. So Ekman transport is the net transport of water by wind-induced motion. So the overall water movement due to Ekman's spiral, ideal transport is 90 degrees from the wind. Transport direction depends on the hemisphere. Ekman transport is proportional to the speed of the wind. Higher wind, higher transport. So convergence and divergence. Where water converges, water piles up and causes downwelling. And then where water diverges, water level lowers and causes upwelling. So converging surface seawater. Surface seawater moves towards an area. Surface seawater piles up. The seawater moves downward, downwelling. You have low biological productivity. Diverging. Surface seawater moves away. Deeper seawater, cooler, nutrient-rich seawater replaces the surface seawater. This is upwelling. High biological productivity. So upwelling, you have vertical movement of cold, nutrient-rich water to the surface. High biological productivity. Downwelling. Vertical movement of seawater downward in water column. Low biological productivity. So this is going to tell you where this is showing you areas of downwelling. This is showing you a really good area of upwelling. So coastal upwelling, Ekman transport moves surface seawater offshore. Cool, nutrient-rich deep seawater comes to replace displaced surface waters. Other types of upwelling, you have offshore winds, seafloor obstruction, coastal geometry change. As you can see in the pictures right here. Then you have Ekman transport moves surface seawater towards the shore. Water piles up and moves downward in water column, lack of marine life. Langmuir circulation is a complex horizontal helical or spiral motion that extends parallel to the wind. Adjacent helices rotate in opposite directions, creating alternating zones of convergence and divergence. Material floating on the surface becomes concentrated in the zones of convergence and forms sea stripes which parallel the wind direction. So you got some upwelling going right here, you got some downwelling, and then you have your little streaks, you got the wind, and you got the water movement. That's what it looks like. There's your Langmuir circulation. I know y'all have all seen this on some type of lake or something. So vortice is the circulation and vortice are two primary measures of rotation in a fluid. Circulation, which is the scalar integral quantity, is a macroscopic measure of rotation for a finite area of the fluid. Vortice, however, is a vector field. So it's going to have a direction. So it's a microscopic measure of the rotation at any point in the fluid. Vortice is the tendency for elements of the fluid to spin. Vortice can be related to the amount of circulation or rotation, or more strictly, the local angular rate of rotation in a fluid. So absolute vortice. Vortice is viewed as an internal reference frame or integral reference frame. Relative vortice, where it's viewed as the rotating reference frame of Earth. Planetary vortice is associated with the rotation of Earth. And when we talked about Coriolis, we introduced the idea of planetary vortices. Every object on Earth has a vortice given to it by the rotation of the Earth, except an object on the equator. This vortice is dependent on the latitude. We're almost there, guys. So geostrophic balance is the most large currents are in geostrophic balance. All currents are pushed to the right. This piles water up on the right. This creates a pressure force back towards the current, and eventually a balance is reached. Pressure balances Coriolis, as they're showing you right here in the photos. So geostrophic flow, a current that develops out of the Earth's rotation and is the result of a near balance between gravitational force and the Coriolis effect. Ideal geostrophic flow. Friction generates actual geostrophic flow. We understand that? Great. Antarctic circulation. So your Antarctic circumpolar current is also called the west wind drift, and the penguin gyre is the only current to completely encircle Earth than any other current because it goes all the way around the Antarctic continent. Dear Lord, it's been a long day. Antarctic convergence is the cold, dense Antarctic waters converge with warmer, less dense sub-Antarctic waters. The northernmost boundary of the Antarctic Ocean, so your east wind drift. These are your polar easterlies. This creates surface divergent with opposite flowing Antarctic circumpolar current, and your Antarctic divergence is an abundant marine life. Atlantic Ocean circulation. These are your North Atlantic subtropical gyres, North Equatorial current, your Gulf Stream, your North Atlantic current, your Canary current, your South Equatorial current, your North Equatorial countercurrent. Then you have your Atlantic Ocean circulation. So these are your Brazil current, your Antarctic circumpolar current, your Benguela current, and your South Equatorial current. Gulf Stream, most important of them all. Best studied of all ocean currents. It meanders and loops. It merges with the Sargasso Sea, which circulates around the center of the North Atlantic gyre. Its unique biology, sargassum. It's a big pile of seaweed in the middle of the ocean that is very important to marine life and reproduction and all this other good stuff. We'll get into it later. So, Gulf Stream, it meanders through loops. It may cause loss of water volume and generate warm core rings. Warmer Sargasso seawater trapped in loops surrounded by cool water. Cold core rings. Cold water trapped in loops surrounded by warm water. Their unique biological populations. You can see some curlicues right in there with some core rings. Oops, nope, we missed one. So then we have the Labrador, the Ininger, I don't know how to say that, and then the Norwegian current and the North Atlantic current. So, north moving currents, you have the Gulf Stream, which warms the east coast of the U.S. and northern Europe. Then you have the North Atlantic current with the Norwegian, and they're warm with the northwestern Europe. And then you have south moving currents, they're cool. Labrador cools eastern Canada, and the Canary cools North African coast. So monsoons, seasonal reversal of winds over northern Indian Ocean. Heat capacity differential, northeast monsoon, winter, and southwest monsoon summer. Then you have the Indian Ocean circulation, and your Indian Ocean monsoon, it affects seasonal land weather, affects seasonal Indian Ocean current circulation, and affects phytoplankton productivity. Indian Ocean circulation is a subtropical gyre. You have the Agulhas current, Australian current, and the Leeuwin current. Then you have the North Pacific subtropical gyre. You have Kuroshio, North Pacific, California, North Equatorial, and Alaskan. You have more of those that we're just not going to get into, and then here's some more. And then you have ocean versus atmosphere. Both are shallow, thin layers of fluid. Both are rotating rapidly. Both are stratified fluids, usually stably with lighter fluid on top. The ocean has sidewall boundaries. The ocean has a definitive top while the atmosphere does not. The ocean is almost incomprehensible. The ocean is driven primarily by thermal forcing at its lower boundary. The oceans are driven primarily by mechanical driven from the top. Winds, duh. We already talked about that. So the atmosphere has significant internal diabatic heating or latent heating release radiation. The oceans do not. The oceans are salty. The atmosphere is moist and cloudy. The ocean is dense. And there's a large heat capacity with large inertia. 2.5 meters of water holds as much heat as the whole depth of the atmosphere. So atmospheric ocean connections in the Pacific Ocean. You have the Walker circulation cell. Normal conditions, air pressure across equatorial Pacific is higher in eastern Pacific. You have strong southeast trade winds. You have Pacific warm pool on the western side of the ocean, thermocline deeper on western side, and upwelling off the coast of Peru. That shows you what the Walker cell looks like. So El Nino is a warm surface current in the equatorial eastern Pacific that occurs periodically around Christmas time. Southern oscillation is the change in atmospheric pressure over Pacific Ocean accompanying El Nino, and we'll get all into, I think, this much deeper later. Then El Nino ENSO describes a combined oceanic atmospheric disturbance. And then La Nina is a climate pattern that describes the cooling of surface ocean waters along the tropical west coast. And La Nina also is considered to be the counterpart of El Niño, which is characterized by unusual warm ocean temperatures in the equatorial region of the Pacific Ocean. So Walker cell circulation is disrupted. High pressure in eastern Pacific weakens. Weaker trade winds. Warm pool migrates eastward. Thermocline deeper in eastern Pacific. You have downwelling, and then you have lower biological productivity. And then we have a picture. We're almost there, guys. So La Nina is the increased pressure difference across the equatorial Pacific. Stronger trade winds, stronger upwelling in eastern Pacific, shallower thermocline, cooler than normal seawater, and higher biological productivity. And then you have occurrence of ENSO events. El Nino warm phase about every 2 to 10 years. Highly irregular phases usually last 12 to 18 months. 10,000 a year. Sediment record of events. ENSO may be a part of Pacific decadal oscillation and long-term natural climate cycle lasts 20 to 30 years. There's your cycle. These are your global impacts. Notable ENSO events, 1982 to 83, 97 to 98. Flooding, drought, erosion, fires, tropical storms, harmful effects on marine life, and they are very unpredictable. So, you have the Tropical Ocean Global Atmosphere Program, and it monitors the South Pacific in a system of buoys, and the Tropical Atmosphere and Ocean Project also continues monitoring, and ENSO still not fully understood. So, you have density structure of the ocean. Ocean is divided into 3 zones. You have surface zone, you have the phenocline, and you have the deep zone. So your surface zone is the upper layer of the ocean. It's containing the least dense water. The surface zone is only about 2% of the total ocean volume. Phenocline is a zone which density increases with depth, containing about 18% of all ocean water, and then 80% of all ocean water is in the deep zone. There's a little change in density throughout this layer. There you go. So you have your surface zone, your phenocline, and your deep zone. Deep ocean conditions. You have cold, still, dark, essentially no productivity, sparse life, and extremely high pressure. Thermohaline circulation is deep zone circulation driven by temperature and density differences in water. It's below the phenocline. It's 90% of all ocean water, and it's slow velocity. Thermocline circulation. It originates in high latitude surface oceans. Cooled, now dense seawater, surface water sinks and changes little. Deep water masses identified on temperature salinity diagram identifies deep water masses based on temperature, salinity, and resulting densities. Then we have a picture of all of this lovely, lovely stuff. And then we have more pictures. And then thermohaline circulation, some deep water masses, your Antarctic bottom water, your North Atlantic deep water, your Antarctic intermediate water, and your oceanic common water. These are cold surface seawater sinks at polar regions and move towards the equator. A current that connects the ocean surface via upwelling and downwelling. This is your conveyor belt. It's also called a thermohaline circulation. It mixes waters within and throughout all oceans. Oxygen flows down, nutrients flow up. There's your conveyor belt circulation, more conveyor belt circulation. So, currents carry more energy than winds. Florida Gulf Stream current system, underwater turbines. And we are done. Thank you for sticking with me for the last 30 minutes. I know this was super boring. We're going to be here for a while because we just covered a lot. And y'all got quite a bit of vocab to do. So, have fun. I'll talk to you in the next lecture. If you have any questions, please feel free to reach out. Thanks. Have a great day. Bye.